Good morning, everyone. Today is October 23, 2020, and today is lecture number 26, E524 Digital MOS LSI Circuits. So we were talking about the chapter called Sequential Logic Circuit. In which we were studying the static latches and flip-flops, right? In that also, like we studied that there are three important parameters. One is called setup time, hold time, and and propagation delay, which are playing the important role over here, right? So there is only one small correction. Last time when I was talking, I made a mistake over here that if it is a mux based positive or negative latch, there are 4 transistors and nobody has corrected me. I thought it's 8 transistor and I wrote 8, but there are 4 transistors, 1, 2, 3, and 4 transmission gate. So clock is driving 4 times CZB, not 8 times. So that was the correction. And because of this loading issues, we moved to the pass transistor based topology where such kind of structure is there, right? And we also learned that if this is going to be acting as a, let's say, setup time, hold time, and all these things, we know that the propagating from this point to this point is required 2 TP inverter plus 2 TP transmission gate. Other than that, the signal which is available before the clock starts, it's almost at TP of inverter. And if I am looking for TCQ, contamination delay, it's going to be equal to the after clock, how much time it takes to transfer the logic which is available here to the cube. So in that case, it's going to be equal to T propagation delay of inverter plus propagation delay of transmission gate. So we studied all these things, and we have analyzed, and we also know that because of all these, like we have to decide what should be the clock frequency and all these things. And afterwards we have studied the master slave topology. In master slave, you can have uh, positive latch and the negative latch together, which are going to be act as a flip-flop, or you can say that it's a resistor where it's age triggered. If you want to make positive age trigger or negative age trigger, accordingly you can choose which one has to be there, right? So all these things we have already studied. Now let's go inside the master slave using transmission gate. But before that, just for your information, I am drawing the mux based circuit which we have done already last time. Right, so this is what happening in the master slave flip-flop. Right, now I want to implement this thing inside that one. So how does it look like? So if you remember, So this kind of positive or negative latch has to be connected, which is being done over here. You can see here the first part, which is here, it's a negative latch because this is clock. When clock equal to 0, this is off. When clock equal to when it's 1, this is off. But when clock equal to 0, this is working. So here we are implementing clock bar, right? So here it's a clock bar, here it's a clock, here it's a clock bar. So accordingly, the first one is going to be connected, and that is how it works. So that is the negative latch, and this is the positive latch. Combination of both, you are going to have the flip-flop, right? So okay, so already the functionality is known to us. However, I want to know that 3 important things, which are setup time, hold time, and propagation delay. So if we are talking about the setup time, the clock, so as per the definition, before clock, how much time before? The D input has to be available. That is going to be known as the setup time. If it is more than that, if it is more than that, it's okay, fine. But if it is lesser than the required setup time, the problems will be created. We will discuss that also in the next slide. But before that, if you need to find out the setup time, we understand that when clock is going from 0 to 1, so clock is actually when you are going here 1, this is going to be off. But when you are going to give the clock 0, this is 1, and similarly this is 0. So this is on right now, and it's available over here. But note that the output Q is available only after this clock is going from 0 to 1. So when clock is going from 0 to 1, when it's in 1, you are going to have the output, right? As per this whole thing known to us. So, and whatever has been sampled at 0 or in the latch condition, this whatever the value is latch, it's going to be available at the output. So you can see that the green path is showing that before clock is moving from 0 to 1, you need to following transmission gates and the inverters. Means in a line there are 3 inverters, 3 propagation delay of inverters plus 1 propagation delay of transmission gate, right? So if you are having this propagation delay and this is well enough, then this D input will be available here. Of course, it's a D bar, or you can say that QM bar, but the input is available here when the clock is moving from 0 to 1. Before that, whatever is happening, it's not going to happen, right? So this value has to be available much before this time is going to be make the settled value of D. So this is a setup time before which this will make the connection from here to here. Notably, if you are looking at the second part, where when this is going to be available at the output, that was the first part, but the next part is the one when this latch is going to be there, and at that time there is no role of this input at all because this transistor is in off mode, right? So to get this output other side, it does not require any time to go that side because already input was available. When this is off, It does not matter how much time it has to hold. So ideally, even if it's like 0 seconds, it's okay, fine. So as per this structure, hold time requirement is 0. Setup time requirement is on green color path, which is going to be 3 propagation delay of inverter plus propagation delay of transmission gate, right? And this is if you want to find out now the propagation delay. So propagating the value from maybe this point to this point or this point to this point, which point you are interested. If you are interested in contamination delay, contamination delay depends on the fact that, look, this value will be sampled over here already, and thereafter you're going to see the output. So in that case, you can see, if you are interested in contamination delay, the brown path will be followed in the worst case. So contamination delay says that the D input is already available after the inverter's thing, and that is going to be transferred over here. But notably, if you understand one more thing, that contamination delay has following definition. So setup time says that I have to be available before time. That is the setup time. Hold time says that the value has to be hold for some time after going from clock 0 to 1. But other than that, after going this clock from 0 to 1, how much time it takes to propagate to get the Q value? That is the contamination. So if you want to find out, you can see actually the value starts after the propagation delay, which is for the setup time. So if you are considering from here, it's getting the overlap over here. So it's a better thing that you have to start after the propagation delay is actually calculated after the setup time. So setup time is till this point. You can see over here, it's still this point. So after that only you have to calculate the contamination delay, because if you are calculating the previous value also, which is part of setup time, which was coming much before the clock is going from 0 to 1. Clock is moving from 0 to 1 over here, by the way. And after that only we have to start calculating how much time you will have to get the output. So on a critical path, this yellow line will be there, not the brown line which I was drawing earlier. That was just for your information. However, that will not be there. So in that case, the contamination delay is going to be equal to the propagation delay coming from transmission gate and inverter I6. So you can write down this, right? So this is the contamination delay, right? And this is how you can find out the things as required. Okay, now let's assume that you have, okay, it's better to draw over here, because even though I'll clean it and then I'll draw over here. The setup time is equal to something like 210 nanosecond is there. It's already there. And what I'm doing, that I'm giving the D input. So this is the D input, and let's assume that this clock, which is in red, is coming after much after, you can say, more than 210 nanosecond, which is already the setup time. We decided that it's meeting that. Okay, if you, from all these numbers, I know that it's going to be more than that. That's why I kept it here. So if setup time of this circuit is 210 nanosecond, if I am giving the enough time after the D is going from 0 to 1, what is going to happen? So D is going from 0 to 1. What is going to happen at that time? That QM is also, you can see here, QM is also 0. Look at this, there are two inverters, and when there is a path from here to here, in that case you are going to have QM equal to D. So QM is 0, and during that time, note that Q is equal to 1, because sorry, Q is equal to, also equal to 0 in that case, right? So QM and Q are same. But right now, let's talk about just QM, and then later we'll talk about other things. So one more thing is there. Here there is a point, let's call it X. X and QM are complementary to each other. So X is somewhere here with value of 1. So if it is, you are having this 0 to 1 transition, you can see here 0 to 1 transition is starting after here, this point, or you can say after the midpoint. This inverter is going to start making this negative one, right? It's going, this has to go from 1 to 0, and same will be transfer over point X, and at that time QM QM has to take this point and going upside. So QM is going upside and this is going downside, right? And because of the available propagation delay more than which is required in our case, which is going from like 2 TP of inverter plus the propagation delay of transmission gate, adding all this, whatever is coming, if it is available at that time, this is going to be settled at 0 and this is going to be settled at 1, right? Because it has the enough time, and accordingly the Q will be also going from whatever the value earlier was, but now Q value will also be equal to 1 after propagation delay, which is contamination delay from here to here, and you have 1. So this thick line is Q, right? So QM and Q are same, but they are going to be same after some time. They require some time, which is TCQ. Okay, so this was all about this circuit, and it's giving you the correct output. If you are going from 0 to 1, this is also 1 at the settled value. But what if I am saying that D is going high, 0 to 1, clock is going also 0 to 1 high, but smaller than the setup time, right? So if it is smaller than setup time, what is going to happen? So when this is 0, look at the first part, when D equal to 0, this is going to be 1. So this is 1, which is the case for, let's say, point X, and for the case of QM, it's again at 0, right? The QM is also 0. But what is happening when this is moving from 0 to 1? Note that at that time this clock is not there. Okay, so because of that, when the clock is 0, because of clock is 0, there is a path, right? In that case, during that time, when it's going from higher value of the switching threshold, this X value is going to go down. But here you can see that of this state of clock, which is the case, then this transistor is getting off and there is no supply of data. It's latch condition, and in that case you are going to have this loop only, right? So this value remains at the place where it was. So when it's going there, it's remain at the place where it was, right? So at this point, and same way QM has tried to go up, but somewhere at midpoint it's also stopped, because at that time I stopped supplying the value of going from 0 to 1 here. So in that case, what is happening? So only the rate path which is available here, that's going to be there, and at the QM it's there. So what is going to happen in this case? This X is going to be considered as noise margin high, right? And this is going to be considered as noise margin low side. So high will go towards high side and will settle at 1, means node X, and QM is going to be down and settle at 0. So even though there is a flip from 0 to 1 for the case of D input, there is no flip from at the case of QM, and because of that, Q, which was expected to go to 1, but after this point it's going to be at 0. You see? So this is happening because there is not enough setup time I have given to the circuit. So if I give setup time which is 210 nanosecond, if it is greater than or equal to 210 nanosecond, then you are going to see the correct output. However, if it is not, in that case you will get the wrong answer or the faulty output. Same can be seen over here. So same you can read from book called Rabe, so it has been taken from there only. So it is showing the same results, and you can read the related text accordingly, so you can understand how it works. Now let's understand one more thing. In the case of the previous one, where okay, the most important part over here is you can see there are clock is driving 8 transistors, 1 2 3 4 5 6 7 8. So clock is driving 8 transistors. So 8 transistors are going to be acting as a load over here. You can see here 8 transistor, here 8 transistor. So in that case the load is 8 times gate capacitance of these transistors. You can call them as 8 CGB. If all are identical, you are going to have 8 CGB as a load, right? So if you want to reduce it, what I can do, I can remove the switching which is happening in the feedback. If I remove these transistors, what is going to happen? It will look like this one, right? So first you are giving input to the bistable latch circuitry. This is happening when the clock equal to 0, and when it's going from 0 to 1, it's another latch which is positive latch. This is a negative latch. Connecting both of them in a cascade manner, you are going to make the flip-flop, which is positive edge trigger, right? So this is what we are making over here. Now we have to understand following things, that if it is a negative latch, when this is 0, clock bar is equal to 0, this is 0, right? So both the transistors are going to be on. When clock is 0, both the transistors are on and stopped here. Look at this. At that time this particular switch is off. Notably, this is also going to be there, right? So in that case, the effective time which is required to propagate from here to here, I'm just talking about the propagating signal from here to here, it's going to be equal to the propagation delay of transmission gate plus the propagation delay of this inverter, or I2, depending on whichever is the worst one, you are going to take that one. But in this case, the best part is, like, this is the latch condition, and it's going to give you guarantee that the output is coming here, the saddle one. But while doing this, there are two inverters. I could have done this also, just one inverter and one transmission gate. I could have done this, but I have added one more here inverter which is in positive feedback, which will make sure that even if there is some noise around the VDD by 2, it's going to be settled at two stable point A and B. If you remember the characteristic which we have already studied for this one. So if you are around the metastable point C, the output will be either A or B. So this guarantees that output is either A or B because of the positive feedback. If it is open loop, you don't know what is going to be output, or it's not going to be the stable one. It's require the latch latching the required signal. So that's why this is the advantageous part over here, and that is what we are adding. So this is happening when it's clock equal to 0. When clock equal to 1, which is the next part, when you can see here D bar is available over here. By principle, after the propagation delay of inverter plus the propagation delay of the transmission gate, D bar is available after that. And when the clock is getting high, means earlier it was 0, now it's 1, then look at this, this particular path is on, right? Or you can say the whole this path is on, but this part is actually off. So now there is no supply of D input. However, whatever the value was available, which is D bar, same will be transferred at the other point. So let's assume that this is D bar over here. Same should be transferred over here after the time of propagation delay coming from the propagation delay of transmission gate and the propagation delay of the inverter, right? So here the main thing is, so D bar is here, and after that propagation time, same thing will be available over here. So this is a positive age triggered flip flop where D is going at the output. But there are lots of problem over here. When you are designing this, the reduction of the gate capacitance of clock is actually decreased by 4 transistors, and you are going to see the load of 4 times gate capacitance of those transistors. This is one thing. Next thing is, when you are transferring from here to here, you can see that this okay, I'll take another color. Maybe this D can go from here to here also. And look, this who told you that you are going to follow only the direction from left to right? It might happen that there is a possibility that you can go from right to left also. Means signal is going to find its own path wherever there is a shortest path with respect to the resistance. What I mean to say over here is, look, if there is a switch when this clock bar equal to 0 and this is clock, then this is 1. In that case, you are saying that whatever I am applying here, that will go to the next side. But when you are going to make this on, there is also possibility that whatever is available here, it can go this side also. It's a bidirectional thing. It's not compulsion that it is going from here to here only. It can come from here to here also. But it's depending on the fact that which side it sees the smallest resistance. Okay. So before going to that, like just for understanding completely, although it's not, I would say that the complete thing, but without understanding this, you will have problem. Let's understand following things. If there is an NMOS and if there is a PMOS, you must be knowing that if you're going to be seen inside the gate of any transistor, so the gate impedance is equal to infinity, right? This is already known to us. It sees the infinite impedance. If you are looking at the source side, look, wherever there is a arrow, it's going to see 1 by GM. Looking at drain side, you are seeing channel length modulation resistance RO, right? So if this is the case, just remember this and you can understand that in this case 1 by GM is much smaller than R0, and R0 we are calling it as high impedance, by the way, and 1 by GM we are calling it as a low impedance. Now if that is the case, let's look at the inverter one more time. I am drawing this inverter with the analog symbol where there are arrows so that you can understand what is going on. Okay, so now if this is an inverter, if I am looking into this inverter, what will be the impedance? So impedance at gate side, I am going to see infinity, right? Because there are two infinity in parallel, so infinity. If I am looking here at drain side, just look at this drain side, I am going to see RO. So at drain side, when I'm looking up and down, I'm going to see RO upside, RO downside, both are in parallel. So around RO by 2, that's the impedance looking at the output. But we also 1 by GM, low impedance, and already infinity is also high. So at input, there is high impedance, and here it's low impedance. Right? So the base case for transferring the voltage is it has to be like input side, the infinite impedance, and output side, there has to be again infinite impedance in the case of inverter. But the thing is not exactly like that. I want that this is going other side, right? I want this one going other side. And in this case, when there are this guy should go, transfer to this side as per the normal way. But in a case when there is a possibility that there is a low impedance over here, that path will be taken first of all. So look here now, again one more time. When this D bar is available over here, and when this T2 is switch is on, you can understand that D bar will go here. But at the same time, when it's passing through here, D is connecting D bar. Then look at this this particular inverter. that can also travel from here to here, right? There is a possibility. So to avoid this, what we can do, we need to make sure that when it's looking inside this, there has to be high impedance compared to looking at the impedance which is over here. So impedance over here has to be very high and this has to be just high. You can't avoid it because still it's seeing at the gate, right? And same thing for here. I want to make this resistance much lower than the resistance looking at this output. So this has to be high. If you want to do that, what is the best way? The best way is, let's make the rule that W by L of I2 and I4 has to be minimum, or let's not I should, I would say that the one which is going to give you the lowest resistance. Sorry, it has to be highest resistance, right? That was decided. Sorry, that was a mistake. So how to get the highest resistance? If you remember, as I am increasing the W by L of a transistor in an inverter, the resistance is going to be decreased. If I want to make the high resistance, I need to keep, let's say, if there are various possibilities are there. One has 130 nanometer, or let's say 220 nanometer divided by 130 nanometer. One is 500 nanometer by 130 nanometer, right? So in both the cases, this one has lower resistance. So if I'm keeping W as low as possible, so W has to be minimum. And at the same time, if you are so much greedy that I want to make this path completely off, or minimum one where the interaction is debar to, like there are I2 and I4 should not interact much to each other. In that case, L can be also increased. Now look at that, as you are increasing L, and when we also learn that looking from drain side, I'm going to see RO. If I want to increase RO, what I need to do? I need to tweak the L. So if you are doing that, the resistance is going to be increased, right? So that is what we are doing, and that is how we need to design this W by L of this particular chain. It looks very simple, but I1 and I2 may have the ratioed logic which we have done in the previous chapter of CMOS inverter. The W by L of I1 and I3 has to be high to match the resistance, whereas in this case W by L of I2 and W by L of I4 has to be as low as possible, right? So this is what we need to do to design the efficient sequential circuits. And just to make sure that there is no interaction in a reverse thing. Okay, we also studied the same thing as a charge sharing thing, that when this particular transistor is on and then after going in off state, it's going to find out the low resistance path where it can dump the data. I mean to say that when this transistor is off, but still beneath of this there is a channel was already created. When you make it off, still there may be some path, so this charge should go somewhere. So it can go this side or this side depending on the resistance path, right? So, but notably, okay, just to extend the knowledge what we are working with, if there is, you might ask that, let's make the simple small single switch so that there is no confusion. So you might ask that if there is a clock, whatever is available, let's consider this one as capacitor. You're saying that here I was giving some input. When clock was high, no problem. Clock. So the input is available at the output side, the sampled one. Let's call it the sampled input. But when the clock is going from 1 to 0, initially there was some charge beneath of this one. So this charge has to be removed as per the, it's like if so there are two paths. This charge will go here or this charge may go here. But what is happening, in such cases from where we are giving this input from function generator, whose output impedance is around in 50 ohm, which is much lower than the impedance looking in this side, then all the charge will be attracted by 50 ohm and it will be grounded in the function generator itself, right? It won't go this side. But the case when it's like this, when other side is not function generator who is going to take care of your charge, then such things will happen, and that has to be taken into account. And we have to stop these inverters to work in the reverse one. That is known as the reverse conduction. So that reverse conduction possibility needs to be removed. Okay, and that is possible by making W by L of I2 as low as possible and W by L of I1, I3 as high as possible. Sometimes some people are making L very high with minimum width. So as long as you are doing this, such things won't happen. In other word, you can say that this inverter I2 and I4 are weaker transistor, whereas I1 and I3 are stronger one. When I'm saying stronger, it's related with the resistance offered by that particular inverter. In the case of I1 and I3 where resistance is low and W by L are high, you are going to have the stronger behavior. Means they can transfer the logic from 1 to 0 and 0 to 1 very quickly compared to I2 and I4, which are very weak. Okay, so there is one more thing which is creating a problem to us, that till now we have only studied the clock like this. We also talked about the key debouncing and many things, but we have assumed that there is clock and clock bar look like this one, but there are possibility that this is extended inside this, or you can say they're extended inside this. So clock and clock bar are getting overlap. By the way, this one is known as 1-1 overlap, and this is known as 0-0 overlap. Again, this one 1-1 and this is 0-0. If both are overlapping, means both the clocks are on, then again same thing will happen. Means both the transistors are on and there is direct transparent path from D to Q, right? By the way, I forgot to find out the setup time, hold time for this case. Setup time and hold time, you can find out. The setup time is nothing but very simple one. You can understand that when clock is going from 0 to 1 and it's a positive edge trigger, you have to look at the logic before the transmission gate. So before transmission gate, things should be available before the given time, and that's decided by the propagation delay of transmission gate and the propagation delay of inverter. Notably, these two are uh, uh, like in cascaded condition or in latch. So one of them, which is going to give you the worst output, that is going to be considered. In this case, maybe like whichever is worst, you have to take that. So it's about the design criteria, how you are taking this. Critical path. So this will be the setup time. Whole time as like after this going from 0 to 1, when this input is already taken, it does not require anything to be like maintained after that point of time. So t hold is again 0. Propagating this value to this side, you again need propagation delay of transmission gate and propagation delay of inverter. So that is going to be equal to the contamination delay going from here to here. So that's TCQ. Okay, that's the thing we already found out. So here we were talking about this 1100 overlap. If those are there, then there is a direct connection from here to here. So if D is moving from 1 to 0, 0 to 1, same thing will be shown at the output. So it will not be acting as a flip-flop, but it's like a latch. So such things are going to happen. Look at one of the example where there is like old design. If you remember, this is a pass transistor based uh, master slave, where in a feedback there is one switch is there, you can see, right? In other case, the switch was not here, and this was made up with the transmission gate. Here the only problem is, here you are going to see VDD minus VTN, and same way when this is on, because of this pass transistor, you can have the maximum output as VDD minus VTN only. So that is the problem. So if VTN is very high and supply voltage is very low, then such kind of technique, which is of pass transistor, may fail, and we have to design it accordingly, right? This is one thing. Other thing, as it is shown in these two clocks, by the way, there is new term called clock skew. So clock skew will happen when there is a gray shaded area is going to happen when both the clocks are same, either 1 1 or 0 0. Here also 0 0, but fortunately this 0 0 is not affecting the operation of my output. But in the case of when both are 1, like here and here, this is 1 and clock bar is also 1, then there is a transfer, and by the way this is also 1, right? So everything is 1, and you are going to see path from here to here, right? So this was the unwanted thing, but this happened because of the wrong clocks. So the best approach is use non-overlapping clocks, which are like this, where there is enough margin between 1 1. So there are overlap on 0 0 side, which is not affecting your operation of the D register. Then there is no problem, and you should make sure that within this time, even if there is some extra charge will be available on particular node, that will be discharged, right? That will be the T non-overlap, and such kind of clocks are known as non-overlapping clocks. So 1 1 are not overlapping at all. Sometimes if you are using the reverse of that, you can use, with the PMOS transistors, you might have the overlap between 1 1, but there is no overlap between 0 0. That has to be taken into account. So such things you need to understand, and accordingly you need to make these clock phases so that you will have the correct output. For that, you might use such kind of circuit, which is already known to us, where this part is the standard SR, right? So set and reset. The only problem with set and reset was like there should not be the input which are 1 1, right? Any input of OR gate is 1, so output is 0, right? So we don't want that particular thing. So to avoid that, we have the complementary inputs. You can see here there is an inverter over here. Note that I have used one more buffer over here. Why we use it? I keep that question to you, right? Why the buffer has been used over here, right? If you don't use it, what is going to happen? I can remove it also, right? So whatever clock is here, same clock is here. Why we use this clock, this one? You can think about it, right? I'm keeping this question to you. So after this, you can see here there are two back-to-back connected NOR gate, which will make sure that phi 1 and phi 2 are non-overlapping. And this is also very famous in terms of key debouncing circuit also, right? So this is also known to us. Now, if I want to find out the time when I need to check the phi 1 and phi 2, so, or you can say that the propagation delay going from this point to this point or this point. If I'm interested in clock to phi 1 or clock to phi 2, on if I'm going from this side, look, this is passing through this inverter, going through this value. If I take that value, it might be wrong, because there is one more positive feedback is there, which is fade over here. After that, when it's available here, then that's the final value. If you follow this path, you can understand that on critical path, I am seeing the propagation delay of inverter plus propagation delay of the NOR gates. That is going to be my worst case propagation delay to get the phi 1. Similarly, you can find out for this one also. And you will see that it's propagation delay of buffer plus 2 propagation delay of NOR gates. That's the propagation delay required to reach phi 2. So note that I need both of them equal. This is what I'm giving you hints so that you can find out why the buffer has been used. Anyway, so this is where we design the circuits, right? There is one more thing where this is advanced one, but I suggest that like you can analyze on your own. If you see there is some dark part over here, all this dark part indicates that it's a depleted mode transistors has been used. Depleted mode, depletion mode transistors. Depletion modes transistors are 0 VT devices, right? So there is no threshold voltage, but at the same time some high VT devices are also used. So maybe you can analyze it and you can like understand such kind of things are known as the multi-threshold devices or threshold based resistors. So that is what completing our static latch topic. Now onwards we are going to talk about the dynamic latches, where the input is not going to be held for longer time like the case for static. In the dynamic, we are going to hold the value for a small time. It requires a refresh, and the most important part, whatever the static latches we have studied, those are going to hold the value for longer time. However, those values will be valid till the